Ionic bonding.
Ionic bonding is a type of chemical bonding that involves the electrostatic attraction between oppositely charged ions. These ions represent atoms that have lost one or more electrons and atoms that have gained one or more electrons. In the simplest case, the cation is a metal atom and the anion is a nonmetal atom, but these ions can be of a more complex nature, for example molecular ions like NH4+ or SO42. It is important to recognize that clean ionic bonding, in which one atom steals an electron from another, cannot exist. All ionic compounds have some degree of covalent bonding, or electron sharing. Thus, the term ionic bonding is given when the ionic character is greater than the covalent character, that is, a bond in which a large electronegativity difference exists between the two atoms, causing the bonding to be more polar, ionic, than in covalent bonding where electrons are shared more equally. Bonds with partially ionic and partially covalent character are called polar covalent bonds. Ionic compounds conduct electricity when molten or in solution, but typically not as a solid. There are exceptions to this rule, such as rubidium silver iodide, where the silver ion can be quite mobile. Ionic compounds generally have a high melting point, depending on the charge of the ions they consist of. The higher the charges, the stronger the cohesive forces and the higher the melting point. They also tend to be soluble in water. Here, the opposite trend roughly holds: the weaker the cohesive forces, the greater the solubility.
Formation.
Ionic bonding can result from a redox reaction when atoms of an element, usually metal, whose ionization energy is low, release some of their electrons to achieve a stable electron configuration. In doing so, cations are formed. The atom of another element, usually nonmetal, whose electron affinity is positive, then accepts the electron, S, again to attain a stable electron configuration, and after accepting electron, S, the atom becomes an anion. Typically, the stable electron configuration is one of the noble gases for elements in the s block and the p block, and particular stable electron configurations for d block and f block elements. The electrostatic attraction between the anions and cations leads to the formation of a solid with a crystallographic lattice in which the ions are stacked in an alternating fashion. In such a lattice, it is usually not possible to distinguish discrete molecular units, so that the compounds formed are not molecular in nature. However, the ions themselves can be complex and form molecular ions like the acetate anion or the ammonium cation. For example, common table salt is sodium chloride. When sodium, Na, and chlorine, Cl, are combined, the sodium atoms each lose an electron, forming cations, Na+, and the chlorine atoms each gain an electron to form anions, Cl. These ions are then attracted to each other in a 1:1 ratio to form sodium chloride, NaCl. However, to maintain charge neutrality, strict ratios between anions and cations are observed so that ionic compounds, in general, obey the rules of stoichiometry despite not being molecular compounds. For compounds that are transitional to the alloys and possess mixed ionic and metallic bonding, this may not be the case anymore. Many sulfides, for example, do form non-stoichiometric compounds. Many ionic compounds are referred to as salts as they can also be formed by the neutralization reaction of an anious base like NaO with an anious acid like HCl. The salt NaCl is then said to consist of the acid rest Cl and the base rest Na+. The removal of electrons from the cation is endothermic, raising the system's overall energy. There may also be energy changes associated with breaking of existing bonds or the addition of more than one electron to form anions. However, the action of the anions accepting the cation's valence electrons and the subsequent attraction of the ions to each other releases, lattice, energy and, thus, lowers the overall energy of the system. Ionic bonding will occur only if the overall energy change for the reaction is favorable. In general, the reaction is exothermic, but, for example, the formation of mercuric oxide, HgO, is endothermic. The charge of the resulting ions is a major factor in the strength of ionic bonding. For example, a salt C plus A is held together by electrostatic forces roughly 4 times weaker than C2 plus A do according to Coulomb's law. Of course, the sizes of the ions and the particular packing of the lattice are ignored in this simple argument.
Structures.
Ionic compounds in the solid state form lattice structures. The two principal factors in determining the form of the lattice are the relative charges of the ions and their relative sizes. Some structures are adopted by a number of compounds. For example, the structure of the rock salt sodium chloride is also adopted by many alkali halides, and binary oxides such as MgO.
Bond strength.
For a solid crystalline ionic compound, the enthalpy change in forming the solid from gaseous ions is termed the lattice energy. The experimental value for the lattice energy can be determined using the Born-Haber cycle. It can also be calculated using the Born-Land equation as the sum of the electrostatic potential energy, calculated by summing interactions between cations and anions, and a short-range repulsive potential energy term. The electrostatic potential can be expressed in terms of the interionic separation and a constant, Madelung constant, that takes account of the geometry of the crystal. The Born-Land equation gives a reasonable fit to the lattice energy of, for example, sodium chloride, where the calculated value is 756 kJ per mole, which compares to 787 kJ per mole using the Born-Haber cycle.
Polarization effects.
Ions and crystal lattices of purely ionic compounds are spherical. However, if the positive ion is small and or highly charged, it will distort the electron cloud of the negative ion, an effect summarized in Fajon's rules. This polarization of the negative ion leads to a buildup of extra charge density between the two nuclei, that is, to partial covalency. Larger negative ions are more easily polarized, but the effect is usually important only when positive ions with charges of 3+, for example, Al3+, are involved. However, 2+ ions, B2+ or even 1+, Li+ show some polarizing power because their sizes are so small. For example, Li is ionic but has some covalent bonding present. Note that this is not the ionic polarization effect that refers to displacement of ions in the lattice due to the application of an electric field.
Comparison with covalent bonding.
In ionic bonding, the atoms are bound by attraction of opposite ions, whereas, in covalent bonding, atoms are bound by sharing electrons to attain stable electron configurations. In covalent bonding, the molecular geometry around each atom is determined by valence shell electron pair repulsion vs EPR rules, whereas, in ionic materials, the geometry follows maximum packing rules. One could say that covalent bonding is more directional in the sense that the energy penalty for not adhering to the optimum bond angles is large, whereas ionic bonding has no such penalty. There are no shared electron pairs to repel each other, the ions should simply be packed as efficiently as possible. This often leads to much higher coordination numbers. In NaCl, each ion has 6 neighbors and all bond angles are 90 degrees. In CsCl the coordination number is 8. By comparison, carbon typically has a maximum of 4 neighbors. Purely ionic bonding cannot exist, as the proximity of the entities involved in the bonding allows some degree of sharing electron density between them. Therefore, all ionic bonding has some covalent character. Thus, bonding is considered ionic where the ionic character is greater than the covalent character. The larger the difference in electronegativity between the two types of atoms involved in the bonding, the more ionic, polar, it is. Bonds with partially ionic and partially covalent character are called polar covalent bonds. For example, NaCl and MgO interactions have a few percent covalency, while CO bonds are usually 50% ionic and 50% covalent. In general, when ionic bonding occurs, it is not possible to talk about a single ionic bond between two individual atoms, because the cohesive forces that keep the lattice together are of a more collective nature. This is quite different in the case of covalent bonding, where we can often speak of a distinct bond localized between two particular atoms. However, even if ionic bonding is combined with some covalency, the result is not necessarily discrete bonds of a localized character. In such cases, the resulting bonding often requires description in terms of a band structure consisting of gigantic molecular orbitals spanning the entire crystal. Thus, the bonding in the solid often retains its collective rather than localized nature. When the difference in electronegativity is decreased, the bonding may then lead to a semiconductor, a semimetal, or eventually a metallic conductor with metallic bonding.
Electrical conductivity.
Ionic compounds, if molten or dissolved, can conduct electricity because the ions in these conditions are free to move and carry electrons between the anode and the cathode. In the solid form, however, they typically cannot conduct because the electrons are held together too tightly for them to move. However, some ionic compounds can conduct electricity when solid. This is due to migration of the ions, in particular Ag+ and Cu+ themselves under the influence of an electric field. These compounds are known as fast ion conductors.